Now, before we start with the presentation, I would like to point out one thing, and that is that this is a rather method-heavy presentation. And the reason for that is simply that we're going to present results from a modeling exercise. And I think it's kind of disingenuous going through that without actually showing you each and every one of the assumptions that we had to make in order to get to that result. And this is also the presentation that I would have liked to see when I started with this project. So if it helps some kind of fledgling modeler out there, I will be quite happy. So what we're going to do is estimating the emissions and risk of chemical substances released by Swedish households. Now, why do we want to do this? Why don't we just take some kind of environmental sample and look at that directly? Well, first of all, the resolution that we have right now in the modeling, that actually allows the identification of problematic consumer uses, which basically means that we can pinpoint if a compound is used as a solvent, as a softener, or as some kind of food additive, for instance. And also by breaking out the consumer use or the consumer sphere, if that's what you want to call it, that also allows for a comparison to other sources of environmental pollution, such as agriculture or shipping, or basically any other activity that is ongoing. And the end goal here is, of course, that this will allow us to help guide chemical management, making sure that we can spend our resources on those activities where we believe that it has the greatest effect. So we have an extremely simplistic conceptual overview here. We have a consumer who is going to emit something into a sewage treatment plant. You then have emission from the sewage treatment plant into some form of recipient. And we'll start working with the consumer use of chemicals, move into the subsequent emissions, and then go over the sewage treatment, what actually happens there, and then finally end up with a risk assessment of the chemical outflow. See, I'm going to move this because this was annoying. So this is the full conceptual overview of what's happening. And what we are going to start with is collecting data. And that is that we're going to focus on pharmaceuticals, chemicals which we believe get emitted from textiles when they're washed, as well as substances in preparations. Those are our three starting points. We'll then identify all of those chemical structures with each and every one of those compounds, because we need that in order to model the physiochemical properties, which we need in order to do a structure-specific wastewater emission estimate, which we can then feed into a sewage treatment plant modeling, which we can then do a risk assessment of the outflow of. So that is the overview. We will start with the data collection. And we start off with the pharmaceuticals. We have had in Sweden a database which was maintained by the Swedish National Board of Health and Welfare, which contained a number of prescribed defined daily doses. Now, worth noting here is the word prescribed. That means that we're now looking only at prescription drugs and we're emitting everything that is sold over the counter. And that is simply because that data is something that you can get your hands on and you can then later on present it. If you include the over-the-counter drugs, that gets covered by a bit of forced obscurity, so you can't really present the data then. But anyways, that database contained approximately 700 different chemicals. For the textiles, we start off with a database which is maintained by Sverige, and that database contained basically a number where you go, if you have an average piece of Swedish cotton, that cotton textile will then contain approximately 0.1% of compound A, 0.1% of compound B, 0.1% of compound C, etc., etc. And that is then specified down to different fiber types, such as cotton, PET fibers, sheep wool, etc. And that database contains approximately 650 chemicals. Now, last, we're going to look at substances in preparations in Nordic countries. That is a database which contains information on the weight which is used in society. And then that is broken up into so-called use categories. We will go through what that means later on, but it basically means that for each and every compound, you get a 1 ton is used as a solvent, 2 tons is used as an anti-freezing agent, etc., etc. And then there are 54 use categories which we include in this model. And that database contains approximately 2,000 chemicals. Now, this is an overview picture which just shows you the overlap between the cost numbers in the different data sets. And the take-home message from this diagram is just that the three data sets are largely complementary. You have a bit of an overlap between the textiles and the preparations, but we've checked the masses from the different databases and we see that we don't have a large overcounting. So we do have three separate complementary data sets, which we're working with. Now, once we have all of those cost numbers, it's 3,226 in total. We're going to identify each and every one of the chemical structures in order to proceed down this modeling pipeline. And we have one problem that we run into quite early on, and that is that some cost numbers, or in our case, around 15% of the cost numbers that we were working with, actually referred to defined mixtures. So if you look, for example, at the compound 317-34O, that's the cost number, that's immunophilin. 1 mole of that compound actually contains 2 moles of that compound that you see on the right-hand side of the figure, and 1 mole of the compound that you see in the middle of the figure here. So what we needed to do was simply to translate that into the cost numbers for the subparts. So when you have a defined mixture, we're actually taking this into consideration because these compounds behave very differently in the subsequent both sewage treatment plant as well as risk assessment. And I just wanted to go through this because it's not very often you see this split being done. We also had another problem with the cost numbers. We started off with 3,226, and for 2,440 of them, we could actually define a specific structure. So we're losing approximately 1/4 of the data here. And in those 786 cost numbers which we lose, you have a set of compounds which are, for instance, undefined mixtures, either because they're reaction masses or something which you haven't really defined how they look. It can also be that specific cost numbers refers to specific natural products, such as a specific rubber tree extract from a specific region in the world has a specific cost number. Don't really know what that looks like. Can't really do anything in the subsequent steps. And there are also a set of polymers in there. And there we have the same problem that you can't use the same modeling techniques as you do for the organic chemicals or the in the later steps. So we had to exclude those as well. So that is what we lose at this step. Once we boil that down due to that kind of mixture effect that you had, which I showed you for approximately 15% of the data, it actually boils down to only 2007 unique identified chemical structures, which we can push further down our modeling pipeline. Now, the next step here should be the modeling of physiochemical properties, but I won't go through that because it's not very interesting. Once you have your chemical structure defined, you can simply throw that as a set of different models, and it gives you the physiochemical properties of that structure back. Now, for those who have a special interest, I can just say that we used FB-Suite as well as ChemAxon. If you know what that means, good for you. If not, we simply used a set of different models to get the physiochemical properties. So let's instead jump to the structure-specific wastewater emissions. Now, we have a rather straightforward equation which we need to solve. We need to know what the emission to wastewater from consumers is. And for some of the databases here, we need to figure out what the private use is as compared to all the use in the world or all the use that is reported in the database. And we also need to know the emission factor. Now, the emission factor is just a fancy word for the percentage of a compound that is used by a household that you then expect ending up in wastewater. So we need those 3 points in order to actually make an estimate of the emissions from the consumers. And once again, we need to treat our 3 data sets differently because they have different challenges associated with them. For the pharmaceuticals, for instance, we know that all of the use is private. There is no industrial use of prescription pharmaceuticals. The emission factor in turn is then 100% minus the percent which is metabolized, which basically just means that it is 100% minus whatever your body breaks down after you have consumed the pharmaceutical. And in order to get that data, we went through both drug bank and RX list, which is basically just two collections of this type of information to extract that metabolic rate. For the textiles, remember that we started off with a database containing proportions. So basically how many percentage within each fiber types is within each fiber type. And the problem here is then that we needed to find a information on how much textiles that were sold of which types on the Swedish market. Unfortunately, the Swedish Chemicals Agency had a report that contained this information, but it turns out that there's not a perfect overlap between these two data sets, of course. So the information that we had on what's sold on the market, only approximately 46% of that total textile used do we have any information on the chemical content of, because that's the only thing that you have in the Sverige data set that we started with. So we're losing approximately half of the textiles in this step. Now, looking at the emission factor, I have now read more papers on textiles than I thought that I ever would. And it turns out that it's very rare that people do a study where they know what they put into a washing machine and what then also comes out after a subsequent number of washes. So we found only one study which did this, and that was from Luongo et al. In 2016, and they had a range of different compounds which they measured in their original textiles. They washed them 10 times, and then they looked at what was left. So you get a percentage value, which you can use in the modeling in order to get some kind of feel for how much is actually leaching out. So we used that as an assumption for all compounds associated with textiles, and that means that the emission factors for all of the textiles is 30%. For the substances and preparations, there's a little more bells and whistles associated with it. The database contained information on the total chemical content that is used within society and then split into a number of different use groups. That is what you have on the y-axis, so to say, of this table. So you have the different uses. And the problem then was that we wanted to look only at the consumer part. And fortunately, once again, there was a table, which is kind of a translation table, which was created by Breivik et al. In 2012. And what you see in that table is basically that you can go through each of the uses, and then you can associate that use with some kind of sector. So for instance, if you know that a compound is used as a softener, you can then guess, I guess is the fair assumption or fair word to use here, that 0% of that is used in an agricultural industry, while 18% is used in a domestic setting, which is what we're looking for. 32% is used in the polymer industry, and then that kind of table goes on in the other direction here for approximately 15 sectors, which can be associated with the different uses. And then there's one row such as this for each use, and the second row that I have there is just another example. So that gives us the private use. We have the weight from the database. Now we need the emission factor. And those were published by the European Commission in 2003. They also have a set such as this. And once again, we have a number of examples on the right-hand side of the slide. And once again, for those with a special interest, I can say that we updated the European Commission tables using so-called SPERCs, which are simply new emission factors, which are produced by industrial organizations, which take the risk assessment or risk management strategies that they have used into consideration, because they thought that the original table contained too high numbers, basically. So if we look at the examples here on the slide, we can see that for the softeners, there is no differentiation based on the physiochemical properties, but if it's used in a domestic setting, you believe that 90% of the compound goes into wastewater. For the solvents, there's a differentiation based on the vapor pressure, which leads to different emission factors based on what the compound looks like and behaves like. And for the fuels, we have a updated version. It doesn't show here, but it's considerably lower than the fuel emission factors were in the original table. So it has been updated. Now, this was all that we needed in the beginning. And now we got our first results. and the results turned out to look slightly weird. We had a lot of gaseous compounds which in our modeling run looked as if they went into wastewater. And that is simply because of the problem that you see with the softeners here, that there is no differentiation based on the physiochemical properties. So we introduced an additional step after this, which was basically just adding on level 1, which is a model that is developed by the Canadian Centre for Environmental Modelling. And it just describes the environmental distribution of a compound at steady state based on its physiochemical parameters. Basically, it tells you how much of the compound is in, or will most likely be in the air, water, sediment, soil, or a couple of other compartments. And we simply lift away the part that goes to the air in order to get rid of those gaseous compounds in a stringent manner. So now we're done with the structure-specific wastewater emissions, and we're going to move into the sewage treatment plant modeling. We're now in the interface now between the consumers and the sewage treatment plants, and we're now pushing each and every one of these 2007 chemicals through this modeling step, and we look at what comes into the sewage treatment plant, but split into the different use categories. Now, what you have on your y-axis here is the annual emission to wastewater in Sweden, aggregated for the different uses that you see on the x-axis. So what you can see, for instance, is that the largest inflow to the sewage treatment plants comes from cleaning and washing agents, or compounds which are used for cleaning and washing agents. Second largest emission is into wastewater is of bleaching agents, complexing agents, and it goes on like this with different uses. And at the end of your little axis here, you have the pharmaceuticals at the moment. Now, in reality, this is slightly broader, but I've chosen to kind of narrow it down to this because this is suitable to a slide simply. But that is perhaps not that interesting. What we're actually interested in is what comes out of a sewage treatment plant. So we need some kind of sewage treatment plant model on the way here. And what we're going to use is simple TWEEP 4, which was developed by the National Institute for Public Health and the Environment. Once again, this is simply a model that describes the distribution and breakdown of a compound in a sewage treatment plant, once again, based on its physiochemical parameters. This is a program which is used in European Union regulatory settings, as far as I've understood. The only thing that is new here from the previous model that we had to use level 1 is that we now also needed to know the biodegradation rates. And that meant that we needed to implement additional modeling steps to get the biodegradation. But we also went through each and every one of the REACH registration dossiers for the compounds that we had and extracted the biodegradation data from there and used that when there was experimental data available. So we're pushing now still each and every one of those 2007 chemicals which we had, we're pushing them through this model, and we get this thing out. This is the same order of uses on the x-axis, same scale as we had before on the y-axis, just to make things clear. And what you see here is that for some uses, you have a large reduction in the total outflow, while for some uses, you don't have that large of a change. Now that kind of makes sense because what gives a compound good, good properties to work as a cleaning and washing agent is also those properties that might mean that it gets stuck to sludge, for instance, in the sewage treatment plant. This modeling step here kind of looks right. This looks intuitively right, which is nice as a modeler because you never know what you're going to get, but if it looks reasonable, you're kind of happy. So this is what we believe goes out per use, aggregated. Now, that is, of course, not that interesting if we want to look at the risk in the environment. Then we need to do a risk assessment in order to know how much potential problems can you get from these compounds, because tonnage isn't a very good predictor of that. So now we're simply going to take for each and every one of those 2007 chemicals which we had, we're going to take the concentration that we modeled that we have in the outflow, and we're going to divide that with what we call in this step an environmental threshold. And that is basically a concentration at which we think it is safe to have this individual compound in the environment. Now, if we take the outflow concentration, divide that with the concentration we believe is safe to have in the environment, we get a risk value for each and every compound. And that simply means that if this value is larger than 1, you need to dilute the compound in order to get to a safe level, for instance. Now, we've done multiple runs with multiple sets of environmental thresholds, but that's ongoing work. So I'm just going to present one set here. And that is when we take all of the thresholds that we're using in the modeling step from the publication by Leo Postuma et al., which was published in 2019, where we simply, it's called species sensitivity distributions for use in environmental protection, assessment, and management of aquatic ecosystem for 12,386 chemicals. And the paper does exactly what the title says. It gives you a way to calculate where the thresholds are. If anyone has a special interest, I can say that we calculated the HCO5 based on all of the chronic data for those which had a suitable, not the lowest quality type of input data for these 12,386 chemicals. For everyone else, we can just be happy that this is where we got the thresholds from. Now, and the output from this risk assessment then, once again, with the risk aggregated for the different uses is what we see here. And we still have the same values on the right-hand side of the axis, which is now the annual emissions to recipients in tonnage, aggregated total values for Sweden. And the open bars are referring to that axis. What we see, however, is that the gray bars, which are associated with the leftmost y-axis, where we have the risk quotient in the STP or sewage treatment plant outflow, is very different from the amounts that goes out. So basically here we see that there is no correlation between the amount of a compound that goes out as compared to the risk that that compound actually exerts in the environment. Once again, this looks reasonable. We know that bioactive compounds are more problematic gram per gram, so it makes sense that the pharmaceuticals gives off a much higher risk. Once again, as a modeler, you're happy when you get to this step because it looks as you kind of guessed that it would. Now, we're just going to break out that bar for the pharmaceuticals and look a little bit at that one. And now we've taken the top 5 contributors to that risk, and we plotted them like this, that you see that the black bars here are the height of the risk that they each contribute with. So furosemide contributes with a little more than 320 times the concentration that we think is safe in the environment in the direct outflow of the sewage treatment plant. We also have ibuprofen, ethinyl estradiol, and paracetamol in this top 5. Now, there are a few things to note on this figure. The first is, as most of you have noticed now, that ibuprofen has a large over-the-counter sales. We know how big that sale is, but we only have the prescription part in here. If we also included the over-the-counter sales, that bar would actually be 6 times higher. The same thing is true for paracetamol, but there we don't know the total sales of over-the-counter drugs. That's one thing. The other thing is that you have a very uneven distribution, which means that very few compounds contribute the majority of the risk, and many compounds are in the mixture without contributing a lot to the total risk. And this is quite classical. Once again, this is a pattern that we very often see, that few compounds drive the mixture risk. The last thing that we can notice about this figure is simply that, at least for ibuprofen, ethinyl estradiol, and paracetamol, those are compounds which are reported in the literature as being causing risks in the environment. So this is kind of reasonable output. And as a modeler, once again, you're looking at this and you're thinking, well, then maybe we're kind of going on for something. Also for all of the other compounds where we have less information. However, we're going to come back to a few caveats here. The left-hand figure here, you've seen before. Remember that we started off with 3,226 CAS-numbers, of which only 2,440 had a structure, and we boiled that down to 2,007 structures in total. That's the left-hand side, what we saw before. On the right-hand side, we see that only 593 of those 2007 structures actually had a PNEC, which means that for 2/3 of the compounds, which we believe are in the outflow of the sewage treatment plant, we can't do a risk assessment simply because there is no data there. If we break this down on the 3 major subparts, we can see that for the pharmaceuticals, we only have 88 thresholds, while there are 528 chemicals for which, or pharmaceuticals for which we don't know when the compound is unsafe to have in the environment. For the textiles, we cover approximately 1/4 of the compounds, and for the chemical preparations, we cover approximately half of them. And this means that if we look at our little overview here, we started off with 3,226 CAS-numbers. We could find a structure for 2,440 of them, which then boiled down to 2,007 CAS-numbers in total, which we could do the whole modeling step for. And we ended up, however, with approximately exactly 593 CAS-numbers for which we can do the risk assessment of the outflow, which is then, again, approximately just 1/6 of the compounds that we started off with. Now, just to bring this together a little bit.
Great, 3 more minutes, Mikael, to wind up.
I have a watch right next to me. If we look then at the each and every one of these data sets have different problems or challenges associated with them. And what you see, for instance, is that if we look at the pharmaceuticals, we have a high amount of accuracy in the input data, at least for the ones that are prescribed. We don't know the over-the-counter part, but we have a good knowledge of the prescription part. There's a very low amount of unknown structures in there because you can't simply sell something which, as a pharmaceutical, if you don't know what it looks like. However, the availability of predicted no effect concentrations or environmental thresholds is low or very low, while the calculated risk is very high. For the substances in preparations, we have a decent or medium knowledge of the amounts that goes in. We needed to introduce a few steps in the middle there, which kind of brings down the accuracy. However, there's a high amount of unknown structures in there simply because there are a lot of unidentified mixtures in there. The availability of the predicted no effect concentrations or environmental thresholds is medium, and the calculated risk of this group in total is also medium. Looking at the textiles to finish is the amount accuracy is very low. We lose approximately half of the textile information just by not knowing what is in the textiles. However, we also have a low amount of unknown structures in there. The availability of the PNECs or the environmental thresholds is still low, and the calculated risk of these 3 groups is the lowest. However, we need to remember one thing here, and that is that uneven distribution, which I showed you before for the pharmaceuticals. That means basically for every compound that you have in your mixture, which you don't know anything about, it could place itself anywhere on that distribution. And there is at least a chance that it might be a high contributor. And you don't know that because you can't make any prior assumptions on that part. So the conclusions for today is for the modeling that especially problematic compounds and uses may be identified by using the model pipeline that we have discussed. However, for large parts of the consumer emissions, risk cannot be estimated because either the use, exposure, or hazard data is missing. Of the groups that we're looking at, the pharmaceutical seems to be the most problematic group, and there is a great need for more hazard data. Thank you very much.